Okay, answer the following questions regarding the decomposition of arsenic pentafluoride. A 55.8 gram sample of arsenic fluoride is introduced to a 10.5 liter container at 105 degrees Celsius. So first thing is the volume is 10.5 liters. The temperature is 105 degrees Celsius, which is 378 K. What is the initial molar concentration of the ASF5 in the container? So here's the deal. We have 55.8 grams. Now remember, molarity, they want molarity. Molarity is moles per liter. Grams is most closely related to moles because of molar mass. And then this is 10.5 liters. And if I stop this problem right now, we would be in grams per liter. And then what does ASF5 weigh? Well, on the periodic table, arsenic is 74.92 plus 5 times 19. And when I do that, I get that the molar mass is 169.92 grams per mole. This has 2 decimal places. This has 2 decimal places. We get to 169.92 grams goes down, 1 mole goes up. Grams cancels with grams. We're in moles per liter. And if you do this on your calculator, you will get 0.313 moles per liter. Remember that 0 is not a final 0. It's not a sandwich 0. It does not count as one of your 3 sig figs. So this has 3, this has 3, this has 5. Okay, next question. What is the initial pressure in atmospheres? Again, this is the gas law. Now, I did a slightly different than they do with the scoring guidelines. So PV equals nRT. They said, what's the initial pressure? So I'm going to solve this for P by dividing both sides by V. So P equals nRT over V. But interesting, now they do this different on the scoring guidelines. Molarity is defined, the unit for molarity is moles per liter, but the symbol for moles is N, and the symbol for volume, so this is the unit for moles, this is the symbol for moles. This is the unit for volume, this is the symbol for volume. And so if you look here, you can also do this. M, N over V is molarity RT, and that's how I did it. M, we just solved for it. It's 0.0313 moles per liter. R, again, I keep telling you this, but I don't know where this is in the order, that in the revision that occurred in 2013, they used to give this 0.0821, and now they give it to 4 sig fig, so the answers might be slightly different. Okay, so liter cancels with liter and moles cancels with moles, and then the temperature is 378 K. And you know, I always get a lot of satisfaction when we're solving for pressure and every unit except pressure has canceled, and I got 0.071 atmospheres. Slightly different if you look at the scoring guidelines online. It's because of this and because of this. They did it a different way. At 109, this is the equation, ASF5, so this would be called arsenic pentafluoride, decomposes into arsenic trifluoride and then just plain old fluorine. In terms of molar concentrations, write the equilibrium constant expression. So, so here's the deal. Kc is the concentration of AF3. Notice it's a 1 to 1 to 1 mole ratio, so there's not going to be any exponents. This is actually a pretty straightforward. There you go. I bet we have to use it. Okay, when equilibrium is established, 27.7% of the original number of moles of ASF5 have decomposed. Calculate this at equilibrium. Okay, so interesting. sometimes I think really smart kids just memorize an approach. Um, if you understand percents, it shouldn't be too bad. Okay, so I'm going to set up an ice chart, and it's using molarity, not pressure. So these are M's, not ATM. And we just figured out that this starts out 0.0313 molar, has to be molar. And in the beginning, there's none of this and none of this. Now, an interesting thing happens. The problem tells you that 27.7% of this goes away. And then these must go up 27%. So what I did first is, what is 27.7% of 0.313? Remember, it's I don't know where this thing is. It's 1 to 1 to 1. Well, and remember, when you do percents, you convert it to a decimal. Well, when I did 0.277, it ends up being 0.00867. This has 3, this has 3, this has 3. I'm going to keep 3. This is going to go down 0.00867. But these are going to go up 0.00867. Remember, those aren't sandwiched. They're not final zeros after the decimal point. And so very important, this comes up all the time, 1 to 1 to 1. These go up, this goes down, because for every 1 mole of this that leaves, 1 mole of each of these comes. Now, when I do this subtraction here, I'm going to get 0.0226, because 0.0313 minus 0.00867. This has 4 decimal points, this has 5, we only get 4. This is going to be 0.00867, and this is going to be 0.00867, because remember, the equilibrium is always where you start plus the change. So 0.0313 minus or plus negative 0.00867. Okay, so calculate the molar concentration of ASF5 at equilibrium. The molar concentration of ASF5 at equilibrium is 0.0226 molar. That's where you get it. Using molar concentrations, calculate the equilibrium constant. So remember, up in earlier we learned that this was the concentration of ASF3 times the concentration of F2 all over the concentration of ASF5. So if we plug this in, we get 0.00867 times 0.00867. If you want to do 0.00867 squared divided by, just going to go back, 0.0226. 0.0226, and pop that into your calculator, and you will get 0.00333. So that has 3, that has 3, that has 3. So we're going to keep 3. This one's kind of weird. Calculate the mole fraction of F2 in the container at equilibrium. Now, mole fraction of F2 means it's the moles of F2 divided by the moles of all the gases. That's just what a fraction. It's not a percent. And so if you go to your sheet again, this is 0.00867. Oh, by the way, I'm going to talk about this. This says moles, not molarity. Why am I putting in molarity? I'm going to talk about that in a minute. And then, remember, that's moles per liter. Now, this is going to be 0.00867 plus 0.00867 plus 0.0226, because this is the molarity of the fluorine. It's also the molarity of the arsenic trifluoride. and it's also the molarity of ASF5. And then this is the molarity of the F2. So the mole fraction. Okay, so if you do that, you will get 0.217. Now, it's a fraction, it's not a percent. So just because you guys understand percents better, I found 21.7% of the pressure comes from the fluorine, but mole fractions are left as decimals, so 0.217. Now, here's the crazy part. Mole fraction is the fraction of moles. Why can you use molarity? Because if you take moles per liter, so let's say 0.00867. And then, so we're using molarity. And then this is 0.00867 moles per liter plus 0.00867 moles per liter plus 0.00867 moles per liter. Oh, sorry, not that. This is 0.0226. Now look what happens is this is a 10.5 liter volume. So is this, so is this, so is this. And so you got a 10. So when you do this, so because this, everything's in the same container, all of the volumes are the same. And so the ratio of the molarity, remember, the volumes are the same. Obviously, the moles aren't the same. 0.00867 is not the same as all these together. But this ends up canceling this, and basically what happens is, well, then the unit moles is going to cancel moles because everything's in the same exact shaped container. The way that ratios work is it's going to cancel. And so the ratio of the molarity is the ratio of the moles.